Transmeta is perhaps one of the most interesting CPU vendors of its time. After spending its first year trying to be as secret as it could, it suddenly then exploded publicity-wise in the late 90s, announcing that it was going to create a CPU that could run the instruction set of every major CPU architecture out there. I mean, that's not quite what happened, but it's an interesting story of how it didn't, and what it did do, and how that changed the x86 CPU market forever. But before we get to all that stuff, I should say this video is sponsored by PCBWay. Fine purveyor of printed circuit boards. Yes, if you've been joining all your components together with little wires, then you might want to consider a printed circuit board. And luckily, PCBWay will take a design that you've made, you can upload it, and they will send you back that printed circuit board in the post, obviously in exchange for money. After all, they have to pay for sponsoring half of YouTube somehow. Now, initially Transmeta began as what's known as a stealth startup, which is a fancy way of saying they were trying not to attract too much attention. In fact, they were trying to avoid attention so much that they were getting people to sign NDAs left, right and centre. However, this stealth period did not last particularly long, as suddenly Transmeta were out and talking about what they intended to do and making some pretty big celebrity hires. Just on a side note, if you happen to read the Wikipedia article for Transmeta, it tries to make out like they were in this stealth mode until 2000, which isn't true, as there was plenty of stuff in the tech press about them in 1996, and then they had their really big celebrity hire of Linus Torvalds in 1997. And if you want to stay stealth, hiring one of the world's most famous software developers is very, very far from stealth. You will, however, see in the press a lot of references to them being very secretive. But I think this is more a consequence of them trying to build up publicity and hype whilst not yet having an actual processor that they could show to people. We're kind of in the process of making this. Doesn't make for a great story. We're a super secretive tech firm whose new processor is going to revolutionise the world. It's a much better story. But I have digressed. We'll come on to some of their hires later on. Now, the initial idea Transmeta had was to create a processor that could be any of the major CPU architectures that were out there. So while there was a lot of talk about it implementing x86, there was also a lot of talk about it implementing PowerPC and MIPS, possibly even Alpha. But between the company being founded in 1995 and them actually getting a product out in the early 2000s, something very big happened in the IT industry. Intel released a cursed monstrosity that was Itanium. Now, as you can guess from the way I just introduced it, Itanium was not successful. Itanium was not good. Itanium was not cheap. Itanium did not perform anywhere near like what Intel claimed it would. In almost every regard, Itanium was an absolute lemon. But it did manage to do one thing, and it did that one thing well. It managed to scare enough Unix workstation vendors into abandoning their own RISC architecture. HP ditched their PA RISC architecture for it. DEC/Compact/HP, whoever they were at the time, ditched their Alpha CPU for it. SGI moved off MIPS for it, and then moved back when they actually got to see how well it performed. But all the CPU architectures that Transmeta's chip could be, that weren't x86, ended up in an early grave between Transmeta's founding in 1995 and when they got their first product out in the early 2000s. I mean, PowerPC was just about still clinging on, Apple were using it, although by 2008 Apple had announced that they would be moving away from PowerPC. So from the foundation of the company and the idea of we could be any CPU, by the time they got to bringing a product out, there was really only one CPU that was, well, worth them trying to be, and that was x86. Now, Transmeta did a lot of hiring from the open source community. Now, I mentioned their most famous signing of Linus Torvalds, but on the Linux side of things, they also hired Hans-Peter Anvin. I mean, I probably pronounced his surname a little bit wrong, but at the time he was fairly well known for being the person who used to look after the Usenet groups for Linux, and also one of the people behind SysLinux, the boot environment for, well, CDs, PXE, you know, a whole bunch of things. And on the kernel side, he was also responsible for the boot protocol for i386. He also created NASM, which is like my favourite modern assembler. They also hired Stephen C. Johnson, who's probably best well known as the person who created Yak, which was a particularly pertinent skill set for what Transmeta were trying to do. And we'll come on to that later when we discuss how their chip does what it does, where it will be relevant that you know that Yak stands for yet another compiler. But none of these hires were discrete hires. These are fairly well-known people within the technical community, particularly within the Unix community. And Transmeta seemed pretty keen to take publicity advantage of these hires, as there were things in every single bit of the tech press. To be honest, I'm not sure how well Transmeta made use of some of these hires, particularly Linus Torvald, as it seemed they more or less just sort of left him alone to get on with the Linux kernel, which to be fair was becoming a very important thing to let a person just get on with. So there was a good head of steam building up behind Transmeta's publicity, with this idea of a chip that could be other chips. But while the buzz was building, the market around them was shifting somewhat. So what was the plan for how this thing was going to work? Now, I remember there being a number of articles speculating how they were going to do this when they were at the more rumours than fact stage of their publicity, and quite a few of those articles are preserved, so if you're looking at this yourself, do be careful that some articles are more speculation than fact. Now, one of the suggestions was that it was going to use some kind of microcoding solution for doing this, where the CPU would use those microcode instructions to decode the instruction set it was pretending to run into its actual instruction set. Now, that's not how they actually did it, but you can see why that might have been the speculated approach, because at the time, even the likes of Intel and AMD were using an instruction decode phase in their CPU to go from the x86 instruction set that's publicly available to us all to the internal instruction set that their CPU actually ran. So they could have gone for that strategy, and we know that if they had, it would have worked reasonably well for at least x86, because all the x86 processors available at the time did do that. However, they decided that they were going to use a software layer that would translate the instructions of the CPU they're pretending to be into the native instructions that the CPU actually ran. And that native instruction set was based around the concept which was the hot new thing in CPU design and computer science circles. Yes, the very long instruction word. This is the exact same concept that the Itanium processor was geared around. So you can see why Transmeta may not have been making the biggest thing of the fact that they were using that particular technique, as the flagship for this technology, Itanium, had been an epic failure. Pun very much intended. The core concept behind this is that a number of instructions that you want to run in parallel are bundled up into one, well, the term Itanium used, epic instruction. The CPUs then sent this epic instruction, and all the sub-instructions inside it can be ran in parallel. And the idea that the processor does exactly that. However, where Intel's major problem with this was that they were reliant on the compiler to group all those instructions together in advance that could be run in parallel, and the compiler would output a number of epic instructions that the CPU could run. The problem is that requires almost a level of sentience in the compiler to be able to make decent use of that. And although over the decades-long lifetime of Itanium, the compilers got better at doing that, they never got great at doing it. And this is one of the biggest reasons for the failure in terms of performance for Itanium. Now, Transmeta had a different idea. Instructions were going to get grouped together at runtime by the software that was decoding the x86 instructions. So, key to the performance of any chip based around this technology was going to be that translation layer's performance, in terms of how quickly it could convert instructions from one form to the other, but also how well it could eventually group those instructions together. So while like in every other CPU design, how well it performs is based on the performance of the CPU itself, with Transmeta's chips it was going to be based on the CPU performance, but also the performance of the translation layer. And this is why it's going to get fairly difficult to talk about how well the chip they actually produce performs, because its performance is not entirely down to just the chip, but this software layer, and this software layer gives us an oddly variable performance. Because the first time when you load a bit of x86 software, this translation layer translates it one instruction at a time and passes each one of those instructions down to the very long instruction word hardware. So not a lot can happen in terms of improving the performance of this with any parallelization. However, the next time you come around that block of code, well, not only is it cached the instruction translation from non-native to native, it also has some idea as to which instructions go at the same memory locations in sequence, so it knows what instructions it can group together in a very long instruction word instruction. So now, some of the instructions can start running in parallel, because they're grouped into that one great big epic instruction, for want of a better word. And this did seem to perform a lot better than Itanium's idea of work it all out in advance at compile time, as it did have some idea as to how these instructions were used and interleaved from one application to another. But when they did finally produce their Crusoe chip, it came out into a world obsessed with benchmarking performance. And benchmarks results for this thing was really odd. Run it just once, get a terrible score. Run it again, well, it does a lot better. The caching of the instruction translation and also that runtime analysis of what you can group together into a single epic instruction makes a big difference to how well the processor performs. If you're running Quake, for example, it doesn't perform so brilliantly the first time round the time demo, for example. Run it again, well, it does a lot better because there's no code in there that it hasn't seen before. Now, this cache is not persisted onto disk. So when I say run it again, I mean run it again in the same Windows session. We've not shut down the machine and rebooted, because if we do that, well, that cache is gone and it's seeing it again for what's effectively the first time. That cache is also not infinite and is using a chunk of the system's real memory. So if you do too many other things before this chunk of code comes back round again, well, it's just going to run it like it did the first time round. Now, all of this is pretty hidden away from us. We don't load native mode software and then boot up Windows XP, for example. When it starts up, we see something that kind of looks like a BIOS, and it sort of is, because what we have is a firmware that does that translation layer we were talking about, and then it loads a PC BIOS, effectively. We then boot into the operating system just like we would normally. Now, there is a sort of fake device exposed back out to the PC world that lets us monitor and do some control of that translation layer. So when booted into Windows XP, for example, we have a little control panel that lets us manage that software translation layer. For a software-based translation system from one instruction set to the other, it's all remarkably transparent. We don't really ever get to see that in operation. All we see is something that's effectively a PC. Now, luckily, I managed to get a machine based on the Crusoe that we can use to see this thing in operation, because these things are not as rare as you might first think. You may not have heard of Transmeta or their chip, and that's because by and large they just got thrown in regular PC-type devices that came with Windows and were just kind of like all the other PC laptop-type devices. Just it would list Crusoe as your chip. Now, the device I've got here is one of those oddball form factors from the time, something that could be a tablet and a laptop or kiosk type machine, but this processor lent itself quite well to these oddball designs, as one of the things it had going for it, it was very power efficient compared to other x86 chips at the time, which of course meant you could put it in thinner devices because it needed less cooling, for example. So if you're building some form of oddball portable device, where being a bit thinner than normal is an advantage, well, that's a good reason to go for this chip as well as its battery life. So you can see this thing booting up, and again, this is a very normal boot environment. It doesn't look particularly wacky. To your average Windows user, this was just a fairly normal machine. As you can see, it boots into Windows XP, which again, standard Microsoft operating system of the time. And when it finally gets loaded, and I may have skipped a bit of the loading process here, you can see it's just normal Windows XP. Okay, this one's got a tablet form factor, so there's like a pen and touchscreen and stuff. But apart from that adaptation, this is just normal, regular Windows XP. And you can see it's very usable. You know, we just do stuff like we would in Windows normally. And it's not the most performant laptop from this period. I mean, really not. But in general use, basically, it's fine. Transmeta had created themselves a perfectly reasonable x86 processor. Performance-wise, nothing to particularly write home about, but it's not absolutely terrible. Benchmarking-wise, okay, it's a bit wacky. And I promise we will do some benchmarky type stuff later on to show that off. But before I mention this thing, draws less power than chips of the time, or at least competing chips of the time. And that's because it employs two technologies that later on would be common in both AMD and Intel CPUs. Because this is one of the first chips that could scale its CPU frequency. It could also scale the CPU's voltage too. Now, Transmeta would call these technologies long run, and in their second follow-up chip, long run 2. And if you're thinking that this sounds quite familiar compared to what Intel does, well, that's because it is. Lots of companies like Nvidia, Sony, Toshiba, etc., they all licensed the technology behind long run so they could include it in their stuff. Intel, on the other hand, just straight nicked the concept, which would later on go on to be the basis of a lawsuit between Transmeta and Intel, which Intel settled out of court for a very large sum of money. But that means at this time we start seeing it appear in a lot of relatively low-priced portable devices, as you could build a portable device around this thing relatively easily with decent battery performance, and not having to worry about the same kind of thermal conditions that you might get in an Intel CPU also really helped make a more price-sensitive design. There was another factor that limited the performance of the Crusoe as well, and that's the bandwidth of its south bridge. It was relatively low compared to other x86 chips at the time, which could, for example, significantly impact graphics performance of systems based around the chip. There were also some contemporary benchmark tools that just wouldn't run on the Crusoe, which did suggest that maybe it wasn't as x86 compatible as it claimed to be. But performance of the chip did improve over time. Updates to the code morphing software meant that compatibility issues and some performance issues could be resolved in software for existing chip owners. But the chip's reputation had taken a bit of a kicking in the performance circles, so we got a follow-up chip in the form of the Efficient, or at least that's how I'm assuming you're pronouncing it. Instruction-wise, we stick with the very long instruction word architecture that we had before, but this time, instead of having a 128-bit very long instruction word, we moved to a 256-bit very long instruction word, and it also moved to a 90nm fabrication process. Now, all these changes put together made it about twice as fast as the original Crusoe processor, and in fact, Intel's own offering, the Intel Atom, wouldn't get to this level of performance until its 2008 chip, which is 4 years after the Efficient comes out. It's still managing to keep that thermal performance or envelope advantage over the likes of Intel's mobile processor, which was the Pentium M at the time, but it doesn't hit the same performance point in terms of raw computational power. But that thermal envelope again does make it attractive to a certain number of manufacturers trying to make some devices that fit into a certain form factor. But sadly, this is the last chip we'll see from Transmeta. The original high-end chips they thought they could make a mobile, more efficient version of, well, they disappeared out the market and so therefore had the kind of profit margins that Transmeta thought it would make, and it had got itself into the most competitive market in terms of computer chips, that of the Intel x86 style CPU. And it's at a time that the two heavyweights, AMD and Intel, are both creating offerings for the low end of the market in terms of lower price and performance, but better battery life and energy efficiency, right up to the high-end server chips. With both Intel and AMD broadening out their offering, this left a lot less room in the market for the likes of Transmeta. Also, we're just starting to get into the era of the smartphone, so some of the more wacky portable form factors of PC become a lot less popular as smartphones start to eat up all that space. And that smartphone market, CPU-wise, was absolutely dominated by ARM. So there was not really much room for Transmeta in that space either. So, by 2007, Transmeta shifts its focus from being a company that makes chips to a company that licenses IP. And the IP it's licensing is that long-run technology that we talked about earlier that helps manage the power consumption of chips. And this is why at this time we see things like AMD's Turbo Core coming into existence, because they'd licensed the long-run technology. On the power-saving side, we saw Power Now emerge from AMD. Again, same reason. Intel introduces Speed Step and Turbo Boost, and doesn't license them. But in the 2007-2008 period, we see Intel coming to a settlement with Transmeta. In 2008, Transmeta agreed to be taken over by Nova Fora, with the deal being completed in 2009. Unfortunately, later on that year, Nova Fora would collapse due to financial difficulties. Goodness only knows who owns all this technology now. Okay, time for a bit of benchmarking. I said I would come back to it. Now you can see a bit of footage of me running Performance Test version 8, a bit of testing software that still runs on Windows XP, but also runs on more modern versions of Windows as well. So it's written quite a long time after this chip's created, hence it showing CPUs that are substantially more modern than the one I'm currently running the test on to compare it against. And unsurprisingly, it will show that this processor is quite a bit slower than these massively more modern chips, yet still chips that we probably count as retro now. Now, I had thought about doing this as like a whole proper benchmarking exercise and then realised, yeah, most of you probably aren't interested to see that, unfortunately. And also, I'm not particularly well set up to do that and don't have a bunch of comparable machines to put next to it, etc. Also, there are YouTube channels that specialise in this stuff. I'm sure some of you have probably watched stuff from Benchy Test Stefan, where he does an actual good job of benchmarking this sort of stuff. I'll drop a link in the description below if you're interested to see that sort of thing. So, rather than do a half-arsed version of this, what I thought I'd do is I'd let all the tests run, and let all the tests run again, and then tell you, yeah, it's about 15% faster the second time round just on the CPU bits. The graphic stuff doesn't really change in performance at all, because the south bridge of this thing is not very good. So why Transmeta may not have delivered on the initial we can beat any CPU concept, they did prove that they could be a very interesting x86 chip. And the main thing that seemed to stop them doing other architectures was simply there was very little point anymore. We got some very weird and wonderful devices that would simply have not have been possible without this chip's thermal envelope, or at least in the exact form factor we got delivered, and I would not have had a particularly weird time trying to benchmark things. Thanks to Transmeta, we did see a significant improvement in battery life and thermal performance of a number of devices we are a lot more familiar with. Descendants of those technologies are still exactly what's making our processors more efficient today. So, Transmeta did help to at least shape the world we're in now, at least in that one regard, if nothing else. And very few non-Intel or AMD x86 chip vendors can really say the same. They tried to do something bold, different and new, and they did succeed, even if they were never very profitable, or in fact profitable. Now, it does seem a lot of coverage of this chip, looking back at it, is very negative on it, largely based around its performance. But I think a lot of what that coverage fails to do is understand the nuances here, around it mattering how many times you ran the thing when you benchmark it, and just what it was capable of. They also ignore the whole thermal envelope thing. It was a chip made to do a particular job and fit in a particular space and market segment, that when we first get the Crusoe, Intel and AMD aren't really on, and even by the time of the Efficient, AMD and Intel are still way outside of that thermal envelope, even if they are a lot closer than they were previously. In that thermal envelope regard, they're closer to where the likes of ARM were at this point in time, but not doing the ARM instruction set, and also probably not really hitting the same sort of battery lifetime expectations you could get out of an ARM-based system. But also, in that portable space, outside of some use cases for PC-style devices, people weren't that interested in the x86 instruction set. They weren't trying to produce a small PC, they were trying to make a handheld, and it didn't matter if it was PC compatible, for example. If you got all the way to the end of this video, I'd like to say thank you very much for watching. I hope you found our little trip down this unusual technological route in terms of processors interesting, and I'm kind of interested to know what you guys think of the whole concept of this chip in the comments below. If you enjoyed the video, there is a button to indicate that fact. If you didn't, there is also another button of which we will not speak. If you would really like to help the channel out, why not press the subscribe button? It doesn't cost you money, and it makes a big difference as to whether the algorithm will tell people that this video actually exists.